Okay, perfect. Hi, everyone. It's a pleasure for me to be here. My name is Jorge Arce. I am a blockchain and cryptography researcher at Nethermind. So yes, very, I would say, appropriate subject. At least I try to keep it that way for today's event. Today we're going to talk about the role of restaking in sovereign AI agents. So that's a very loaded title. We need to unpack it over the next few slides. That's what we're going to do. In case you're wondering, what on earth does this mean? Okay, so my purpose with this talk is to survey a little bit about these two very important topics to our industry. We have restaking, we have AI agents, and on top of that we have sovereign AI agents. Well, it turns out these topics have been interacting in non-trivial ways over the past couple of months. I wanted to provide a brief survey of where that intersection of those two fields is going, what's the state of the art, what other teams are doing. So we start with a recap. Then we'll talk about the concept of sovereignty, which you may have heard it with other words such as autonomous AI agents, sovereign AI agents. We're all hinting at the same thing. Then we'll talk about the concept of verifiability, which is where restaking comes into the picture, and how it interacts or empowers or allows the construction of sovereign agents. Last but not least, we will discuss some of our future research work we at Nethermind are interested in undertaking with regards to exploring the design space of sovereign AI agents. So without further ado, let's get on with it. First of all, so just for the sake of completeness, probably everyone who has a Twitter account has been exposed to this concept already over the past couple of months, but what is an AI agent? Let us define it as, and this is from one of EigenLayer's blog posts, actually, that I will refer to next, a central orchestrator that manages, in a closed loop, the entire operation that a user wants to perform in some environment. Another definition that focuses a little bit more on the intelligence part, in the ELIZA OS white paper, it's an intelligent system that's capable of autonomously controlling and determining the execution paths under the user's instruction. And so here we have an architecture of an AI agent. This is from Google's white paper on AI agents a while back. And there are some key components that we will refer to, and we will break them down and try to see where it makes sense to involve risk-taking in order to secure these pieces for what we're trying to do. You're always going to have, well, some kind of model, some kind of LLM, of course. That's the AI part of it. You're going to have an orchestration layer, and this can be modularized in different ways. So in the case of this white paper, they propose it as there's a memory, there's a model-based reasoning planning, so strategies that the agent used to reason, plan, execute. There's profile goals and instructions. So all of these wrappers around the LLM itself, right? And there's the tools that the agent uses to interact with the outside world, gain information about it, and execute any actions on behalf of the user. Yet another diagram. This one's from Eliza's documentation. And so we see very similar pieces, so I won't dwell too much into that, right? LLM, the memory, the plugins, as opposed to tools, just different terminology. It's a very new field, so people use different words for different things. For the same things, I mean. And so on and so forth. OK, so let's keep mental taps on the components. We're going to go over them next. The LLM itself, the tools and the plugins to interact with the outside world, memory and state, and then a runtime or orchestration layer that is the glue that keeps everything together. OK, now let's talk about this very, very trendy word about sovereignty for AI agents. What does that mean? OK, essentially it's the idea that we can build agents that are free from external control from any party. And this includes the parties that develop them, that deploy them. This is what we mean with the concept of sovereignty or autonomy. This can unlock some use cases around trust. I will provide a few examples. If we know that we're interacting with an AI agent and there's no human in the loop, then that can help with some trust concerns around working with agents. As an example that is somewhat forward-looking that people have been speculating about for some time is, for example, if you have an agent that needs to be trusted by a collective of people, say the agent executes actions on behalf of a DAO or on behalf of governance, you want to make sure that that agent is not easy to censor by a privileged party, and that it's not in control of a single party that is able to maliciously inject or influence the outcome of the agent's outputs. So this would be an example in which people started brainstorming the need for like, okay, how do we have these agents sort of like become free from this influence, from this outside influence? Two more specific examples. This is some like funny interactions on Twitter. Like I think every single day you see a post by someone calling out AI XBT agent and saying it's not really an agent, it's actually a human. And then it's super funny when AI XBT replies. It just cracks me up. And but think about this for a second. Like AI XBT provides insights on the market. Many people even like invest really like as a consequence of the feedback they receive or like the insight they receive from AI XBT. If there was a human in the loop that could influence this, it's not like financial advice, but that could influence these statements, then perhaps there could be a way for that human to make a lot of money, right? So that would be concerning. And well, some people have looked more deeply into like AI XBT's architecture, but is there a clean way for us to like verify, get some kind of cryptographic proof or otherwise that this agent is indeed sovereign? Another example of an autonomous agent that I learned about from EigenLayer's AI agent series that started like early in the year. It's pretty good watch if you haven't seen it. Pretty interesting to see what people are building with AI agents. This one's called Arto. It's like an AI art collector. It can roast your NFT collection. You can donate NFTs to it, and it's sort of like an art collector of NFTs. When it started out, it had like a couple of NFTs. It didn't have like a big impressive catalog. Today I checked, and it holds like 360K on assets. At some point a month ago, it held over $1 million in assets. And once again, if there was a human in the loop who was just going to rock this, then this whole experiment loses its entire meaning, right? Okay, so we're starting to get closer to this sort of vision of it might make sense to have a world in the future where AI agents interact on par with humans with the blockchain or Web 2 infrastructure that we deal with as humans every day. To say it in other words, a couple of years from now, we may see AI agents as first-class citizens of the digital world. And maybe that's happening faster than we think. And just as a short intermission, at Nethermind we're building for this kind of feature. There's a couple of products or projects we're working on. One is called GigaTrue, which is the Fiverr for AI agents. And so it's like a labor market where autonomous AI agents can advertise their services and actually make a living. And if an agent is truly, truly autonomous and has to pay for their infrastructure, which is pretty much the equivalent for a human paying for their rent, these kinds of markets are going to become important for these kinds of agents. There's also Chaos Chain by Nethermind, which is a layer 2 in which the validators of the layer 2 are AI agents themselves. And they have to come to consensus on what's the blockchain state or the roll-up state transition. So this is already proven to be a very interesting experiment on like multi-agentic environments and what happens when agents need to come to consensus under these conditions. If anyone wants to chat about any of these two initiatives, feel free to let me know. We will have a QR code at the end and you can contact us that way. But the bottom line of all of this, coming back to the restaking and sovereign agents like backbone of what we're discussing, is that to be truly sovereign, these agents are going to need the right infrastructure that doesn't have single points of failure, allows for recovery in the case that there's infrastructure failure or loss of access. Because sure, you can run your agent in a TE, but if you lose access to the machine, then the agent effectively dies, right? And avoiding tampering or censoring by devs or other external influences. Coming back to this point, you can run an agent on a TE, but if it gives you an outcome that you don't like, you may unplug it, and that may be good for avoiding certain dystopian scenarios. It may be bad if this is an agent that has to deal with some kind of transaction or governance decisions that you really don't want to be censored. Thank you. An example on an improvement towards moving to a more like decentralized or less or without a single point of failure architecture for AI agents is Freysa, which you may know from the experiment where they gave it a bunch of money and they gave it the prompt to, or the instructions not to give money to anyone. Someone eventually found a way to jailbreak it, and gained like 40K in the process. Was an interesting experiment in AI safety. But Freysa is also now providing this architecture for people to build their own AI agents and deploy them as a distributed network of TEs that uses like, and it uses like shared secret sharing to share the agent's private key with which it accesses assets and the like. So if a few of these computers go down, the agent can still continue to be operational. So this is a step in the right direction, but it still has like an M of N trust assumption model. We wonder if there's a way to build a fully decentralized architecture for AI agents. Okay. Perfect, we're on time. So next point for us is going to be verifiability and sovereign agents. So appreciate your attention as we're working out through the AI section of things. Let's come back to the restaking section of things. Where does restaking come into the picture? This is what's coming next. Okay, and in this outline, I mentioned two main topics around verifiability. One is verifiable inference, and the other one is, for lack of a better term, I called it verifiable tools. Let's single in on these two topics and what we mean with them. So verifiable inference. This comes back to the idea of people challenging AI XBT and seeing if its decisions actually come from an LLM call. Okay, is there a way for us to prove that you have an input that you feed to the LLM and out comes an associated output? Is there a way to prove that this output indeed comes from LLM inference by a model, given the input that we just described? This is what we mean with verifiable inference. And if we had this kind of proof, like cryptographic, cryptoeconomic, or otherwise, we might have a better time at guaranteeing that there's no human in the loop in our AI constructs. And it's effectively a way to prove the agent's autonomy if we're able to generate these kinds of proofs. So as it turns out, this is an open and challenging problem in general. And there's special things about AI and LLM inference that make it especially challenging. One can attempt to use similar approaches to what you use in just blockchain design, where you have like very heavy computations that happen off-chain and you need to make them verifiable on-chain. But as we try to leverage these building blocks, we run into problems. Let's use the mental model of like a roll-up that is going to be very helpful for this and for something else later on, to try to determine which kinds of tools we have at our disposal to make LLM inference verifiable. If we think about zero knowledge and like ZK rollups, the analog of this, ZK-ML, this is something that is an active area of research. It's quite a challenging problem, and there's some teams working on this, our own cryptography research team as well. But it's still in the early stages and not quite at the stage where you can like generate zero knowledge proofs with like arbitrary inferences with LLM models. There's OPML, SPML, essentially like an optimistic architecture for LLM inference. I'll discuss that in a second more carefully. And there's ZK-TLS. I'm skipping ZK-ML for now. It's an active area of research. It's, I think, beyond the scope of this talk. But it would provide like, I would say like a gold standard for this kind of verification. Now let's think about optimistic LLMs. Imagine that you're performing the AI inference off-chain, and you're using fraud proofs to enforce the correctness. That is, you ask an off-chain operator to perform the inference, and you allow for a challenge period. Anyone can come in, check the inference. If it's wrong, then issue a challenge on chain and have them slashed, potentially. Now, there's like a banana peel that we slip on immediately when we try this, and that is the problem that LLMs are usually not deterministic. That is, and anyone who has played around with ChatGPT knows this, right? You ask it the same question a handful of times, you might get different answers. And this is actually like very ingrained in like a very, let's say, fundamental property of these models, and it's very hard to fight against it. So if you're not getting the same answers every time, how do you even begin to prove that the inference was quote unquote wrong to begin with? Someone else is going to come, try to do a challenge on chain in this optimistic architecture. They're going to get a different answer. There's no way to like, there's no like canonical answer that you could use for a fraud proof. Some teams are working on addressing like building very specific architectures in which you can get back the same results every time, so to speak. But there's many factors involved. There's a random seed that needs to be fixed. Not as much of a problem. The hardware that you're using becomes an issue, in fact. If you run these inferences on different GPUs, you might get different results. And even like the, let's say, accompanying software that you use for the inferences, your version of CUDA, so on and so forth, can make it so that you get different answers. So tricky problem in general. to achieve determinism. Some teams are working on this. Still an open area of research. Okay, now restaking, finally. Restaking and verifiable inference. This is a kind of like right here, right now approach, something that we can leverage in the present to generate proofs of inference. And this leverages the zk-TLS construction, of which we have a couple of AVSs and restaking protocols. It uses zk-TLS to prove that a response to a prompt indeed came from connecting to OpenAI's API, for example. So you get one of these AVSs, opacity reclaim. There's an operator in the protocol that acts as the, let's say, auditor or like certifies the contents of this TLS connection, generates a zero knowledge proof. You can post that on chain or like share that through a data availability layer. And if the proof is not correct, you can get, you can know that the inference was not coming from the purported source. There's a diagram out there describing more or less the details here. This has also been integrated as a PR into ELIZA, so people can start playing with this. Okay, so that's the first half of the picture. 4 minutes. Okay, cool. Thanks. So I'm gonna keep it moving. Verifiable tools for sovereign AI agents. The agent doesn't have like eyes and ears and social cues and context as us to kind of like discern what's right and what's wrong. So it needs feeds of data and oracles that it can trust. And restaking is a way to provide these verifiable data feeds that are secured by cryptoeconomic security. And there's a handful of AVSs that either already exist or are being built that can be integrated with AI agents, say oracles, data collection, data availability, of course, TE networks, all these goodies that will make the life of a sovereign agent easier, because a sovereign agent being sovereign, its next problem is, after, let's say, securing its own architecture and how it's running, its next problem is going to be how to trust how to get information from the outside world to execute its actions in a trustworthy manner. And so the end game is going to be take these pieces of the initial diagram we have, make them all verifiable one by one, the tools, the model. But there's one we're missing, right? And I'm saving this for the end of the talk. The runtime itself, the glue that keeps everything together, that makes the calls, orchestrates them, gets like let's say an audit trail on like the LLM inference was correct, the data that was pulled from the oracle was correct, and if the agent doesn't execute its job correctly, who is to blame? And this is precisely the problem we want to address, and what I'm highlighting as exploring the design space of sovereign AI agents. So we've talked about all of these pieces, but we haven't talked about the glue that holds everything together. And let's try to push the envelope and get as close as possible to the gold standard of like full decentralization and permissionlessness as we can. Consider a construction for an AI engine runtime itself that has all of these properties. It's decentralized, kind of like a blockchain, like Ethereum itself. The operators can opt in and out freely. There's no like federated M of N trust model. Operators can opt in and out. Seamlessly integral with other verifiable modules as well, and verifiable on chain. So one insight when you start thinking about this problem, well, first of all, that sounds like something you might try to use an AVS for. It's one of the tools you could try out. But the more you start thinking about this problem, you realize there's a lot of parallelisms between the problem of building this fully decentralized AI agent and the problem of building a rollup and using decentralized sequencing for this rollup. Let me elaborate on this. So if we could build the AI agent as a smart contract, this would provide the highest degree of sovereignty for the agent. In a way, like smart contract applications are already sovereign, no one can meddle with them, but they don't have this sort of like agentic portion to them. So imagine that we think of the operators of this AI agent as decentralized sequencers that are in charge of computing the agent state transition. The reason this model is helpful is because a lot of the problems in keeping an AI running in a distributed environment also happen in rollups. You need to handle state management because it's too expensive to post the state on chain in order to keep the operators synchronized on what's the state of the rollup. You need to think of even like sharing the proofs of the correct sequencing, so to speak, through a data availability layer. You need to think of how to deal with malicious sequencers and think of the cryptoeconomics on how to disincentivize them from stealing a lot of money on the layer 2. So how do you design the mechanism correctly so that this is unable to happen? So this is one of the next problems we want to deal with and we want to approach. Yes. Here's a construction of these ideas that I have been describing, but you get the picture. There's a variety of open questions and challenges. Reusing existing frameworks, what can we do? What are the slashing conditions? What's the profit from corruption, customer corruption balance? So this is a problem that we are interested in solving and we'll be looking at over the coming months. All right, so if this sounds interesting to you, I'm leaving a QR code. Please connect with us. We would love to discuss building on the AI agent space with you guys. Thank you very much for your attention, and questions or comments, let me know.